Welcome to Essential Problems with CRIP. In this video, we will explore how to write nuclear equations. As we have reviewed already in class, subatomic particles that we will focus on in chemistry refer to proton, neutron, and electron. And the proton has an atomic number of 1. Of course, the atomic number refers to the total number of protons and neutrons within a given nucleus. So for a proton, since it is one proton, the atomic number is 1, and the mass number, which refers to the number of total protons and neutrons in a given nucleus, this is also 1, since it's one proton. The neutron, however, has an atomic number of 0, because it is not a proton. And the electron, not being a proton or a neutron, has a mass number of 0 and an atomic number of -1. The subatomic antiparticles are the same type of particle, meaning having the same mass, but the opposite charge. So here, our mass number is -1 and atomic number -1. For the anti-neutron, the mass number is -1. And for the anti-electron, also called a positron, the atomic number is +1. We typically represent the symbol with a line above it, indicating that it is an antiparticle. Now, what's interesting is that when a particle and its antiparticle collide, it will always yield light. High energy light. So here we have a proton colliding with an antiproton, a neutron colliding with an antineutron, and an electron colliding with an anti-electron or positron. We also have decay particles. So here, alpha decay will refer to the emission of a helium nucleus. We can also have beta decay, which will be associated with a high energy electron. There is also beta plus decay, in which a positron would be produced, and gamma emissions. Let's apply these terms to a variety of nuclear equations. Here we're given, for the first problem, carbon-14 decays by beta particle production to produce. It is absolutely key to do these problems by writing them out on your notebook. So we begin with carbon-14. Carbon is our element symbol C, and 14 the mass number. And the atomic number, looking at it from the periodic table, we are given the value of 6. And notice it decays by beta particle production, meaning we are producing a beta particle. And so we simply look up our beta particle, our high energy electron, and there we have it. So in order to do this, we should find the mass number first. What added to 0 is equal to 14? Of course, this should be 14. What added to -1 is equal to 6? This value is 7. So we have these values. And then in order to determine the unknown element, we look on the periodic table and we use the atomic number. And of course, the atomic number is 7, so this element is nitrogen. Next problem, potassium-40 decays by electron capture to produce. In this case, we are capturing an electron. This is why it is very important to read the problem carefully. Other questions will employ this kind of wording, such as beryllium-9 absorbs an alpha particle, or the nucleus of silicon-29 fuses with a high-energy proton, or lithium-6 fuses with carbon-12 to produce a neutron end. In all of these cases, they are giving us not one reactant, but 2. And so therefore we need to be careful when we're writing these equations out that we write the correct reactants. So 40 plus 0, of course, would yield 40, and 19 plus -1 would yield 18. Looking up on the periodic table, we realize this is element Ar, argon. Next problem, californium-252 decays to produce 4 neutrons, molybdenum-106, and another unknown particle. In order to determine this, again, we need to be sure to indicate that we have 4 neutrons. Now, to write this correctly, we should have 4 as a coefficient next to our correct mass number and atomic number for neutron. Do not put 4 over 0, that is incorrect. These are 4 separate neutrons that are being produced. And if we apply this correctly, we'd realize that 106 added to what number, added to 4 times 1, is equal to 252. And so 4 times 1, of course, is 4. Adding to 106 is 110. If we take the difference of 252 and 110, we get 142. Also, we can see that 4 times 0 would yield 0. So 42 plus what number is equivalent to 98? And so you can see already we have 56. But we would take the difference of 98 and 42 to find 56. And we can look up on the periodic table and discover that this is barium. Finally, we have perhaps one of the most complicated type of problems, but is very similar to what we've encountered here. The complete decay of americium-241 involves successively alpha, alpha, beta, alpha, alpha, beta, alpha, 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 beta, alpha, and beta production. What is the final stable isotope in this decay series? Again, writing out our given, we should add up all of the alpha particles and beta particles that have been produced. Notice there's 1, 2, 3, 4, 5, 6, 7, 8 alpha particles. So 8 helium-4 nuclei. There is 1, 2, 3, 4 beta particles produced, so 4 times our high energy electron. Once we've set it up in this manner, the solution is pretty easy and very much like our previous problem. 4 times 0 is 0, 8 times 4, 32. The difference of 241 and 32 is 209. 8 times 2, 16, plus 4 times negative 1. This would yield 12 total. And the difference of 95 and 12 is 83. Of course, you can always check by adding 83 to 16 to negative 4. And you will see it yields 95. Looking up at the periodic table for atomic number 83, this is bismuth. Till next time, crip.